So this is the Wild T3, and as you can see, it's a much bigger instrument than that of the Wild T2. This one reads an elevation angle only, and it requires or necessitates a phase 1 and phase 2 measurement. It's a little bit, there's a little bit more work involved in calculating the angles, and I'll go over that. What I'm doing here is I'm setting up over this point that was set by the highway department. It has a known horizontal position and a known vertical position. Therefore, I know the height of the tangent plane, or the geometry that I'm going to use in order to measure the Earth. So now we'll take a tape measure and we'll set it right on the top of that guy. And this will allow us to give us a height of the instrument above that point to the center, which I've got a 4 foot, and we're in tenths or decimal feet. And so it's a 474 to the center of the instrument. This is the plate level, and then up in this prism here, you can see the coincident bubble. Both those halves need to make a complete bubble. And this is the target, which is Mount Wrightson. The image in these instruments are inverted. It's just the way God intended them to be. Let's see if I can get a better focus here. A little bit better there. And here is the vernier. This is the micrometer. And I'll go over how to read this off. Let's turn this on. Now you have to do 2 independent readings. What that means is you turn this scalp to where the scale goes all the way and bottoms out left, and then all the way and bottoms out right. And then you line your coincidence lines back up. So I'll take it all the way, and then I'll bring it back into coincidence. And what you do is you read off the angle, and then you double the arc seconds. And if it goes over 60, then you add the, that 60 arc seconds, or 1 minute, to the minutes. So let's take a look at this reading here. Now that we're done in our phase 1 measurement, we're going to rotate the instrument 180 degrees and then do what's called plunging the eyepiece. And we're going to read off the next elevation angle. And we're going to do 2 independent readings of that as well. Here is the target. This is in my phase 2. And now we're going to read off the angle. Now I'm going to do my second independent reading in my second phase. And so I'm going to take this and advance it. And now we bring it back into coincidence and we make our second reading. Okay. Let's see if I'm still on the target here. And we'll go in for a look at the scale. And then I'll go over the scale. Right now we just want to capture it. Quite stubborn. That's a good look. I've now wrapped up. I've turned a total of 3 sets, and so now it's time to take a look at that data. So here's how this works. I started off, I'm in phase 1 on set number 1. This is one complete set here. Here are my 2 independent readings. My first reading was an 8904 32.1. I record that. My second independent reading is an 8904 32.3. I add the arc seconds together and I wind up with, what is that, 64.4? Well, that's over an arc minute, so then I would, or 60 arc seconds, so I then take that, add it to here, the minutes, I end up with 8905, and the arc seconds that are left over is 4.4. And then you turn now into phase 2 and you do the same thing. As you can see here, I blundered here, I forgot to add, so I just crossed it out and rewrote it down here. So when I add these 2 together, I'm over 60 arc seconds, so I then add that to the arc minute, which now puts me at a 9057, 45.2. Now what I do to get the elevation angle is I take both of these zenith angles here. And what I do is I minus out this angle from this angle, and that gives me the elevation angle. And then I subtract that from 90, and that returns the zenith angle. So now it's time to compute the zenith angle. So we take our phase 2, subtract out our phase 1. That leaves us with 1 degree, 52 arc minutes, and 40.8 arc seconds elevation angle. Subtract that from 90, and that returns a zenith angle of an 88 degrees, 7 arc minutes, and 19.2 arc seconds. And now that we have this zenith angle, we can then use some pretty basic geometry to figure out whether or not these angles are matching the expectations or predictions for a flat Earth. So as a field guy, I like to sketch up either a cross section or a plan view of what happened out in the field. So this would be an elevation profile of what happened out in the field today. So I've got 2 different models drawn up here, 2 different predictions going on versus what I measured. And so if you follow this line here, this is the level topographical plane, okay? If you follow this, I believe this is red. If you follow this line here, this is the globe. This is what the Earth does. And then this would be the drop from that. And so this, you should be able to measure this out there with mountain peaks or buildings or whatever. And so that's exactly what I did. I chose a peak. And so I set up over this monument here, which had an elevation of 2895. And then I took a tape measure and I measured to the center of the instrument. And then when you add these 2 together, it provides the necessary requirement that flat earthers talk about, which is the horizontal plane of reference. As you can see here, this is a horizontal plane of reference. Everything's being referenced from here. That's how we're going to get this angle, right? You want to know what this angle is from the reference to the top. And so what you do is you take this total observation height of a 2899 and you subtract it from this 9456. That provides this opposite side of the triangle of a 6556.26. You take this 6556.26 and you divide it by the horizontal plane of reference length, right? Which is this 34.1589 miles. But you got to turn it into feet, hit the arctan, and it will give you this elevation angle of 2 degrees. You take that 2 degrees and you minus it from 90, because if you check it out, 0 up here, comes straight down, straight over, that's a 90-degree angle. So if I subtract this from this, I'll get the flat Earth zenith angle, which was an 8807.05.3. However, that's not what happened. I measured 12 minutes lower. So if the Earth is falling away from the tangent plane, or the horizontal plane of reference, then you would have this drop. Well, this drop is equal to this drop, where flat Earth peak should be and where I actually measured it in reality. This and this are equal to one another. It's just an angle, the same angle over here that subtends, subtends the side of the triangle, which is the opposite side. They correspond to one another. And that's exactly what we saw.